So this is the load that we are talking about, the RF load that we are talking about, which consists of an inductor which is in series with a resistor and a capacitor. The resistor and capacitor are in parallel with each other. The R and the C are in parallel with each other. They are then connected in series with an inductance of 10 nanohenry. So the first part of the question is, what is Z of omega? They don't say anything about finding the value and all. They say, what is Z of omega? Then the part B is, find it at 900 megahertz. That means the frequency is given as 900 megahertz. Then omega is 2 pi f. So once you find this out, you substitute omega equal to 2 pi f in here, you will be able to get part B. And then the final part is it inductive or capacitive? So looking at the question, the equivalent circuit, you see that there is an R which is in parallel with a capacitance, right? So R in parallel with capacitance means R parallel 1 over j omega c. So important thing, Z1 parallel Z2 means Z1 Z2 over Z1 plus Z2. R1 parallel R2 is R1 R2 over R1 plus R2. It's exactly the same thing, but instead of just a real number R, we are using a complex imaginary number Z, Z1 and Z2. The same thing can be viewed as 1 over Z1 plus 1 over Z2. It's the same, yeah? Z1, this becomes my Z1, this becomes my Z2, Z1, Z2 becomes this, Z1 plus Z2 is this. So I end up getting this guy here. It's an algebraic manipulation law, complex numbers. So from here to here, I want to be able to separate out real part and imaginary part together. I don't want to see this j in the denominator there. How do I remove it? I can go ahead and multiply this by 1 minus j omega rc over 1 minus j omega rc, meaning I'm multiplying by a complex conjugate. Conjugate means replace the j by minus j. Conjugate is a star operation law. You're multiplying by 1 minus j omega rc over 1 minus j omega rc. It's as good as multiplying by 1, yeah, but you want to do that so that your denominator becomes 1 plus omega square r square c square, and the numerator becomes r times 1 over this term. After that, all that remains is to rearrange and separate all the real terms together and all the j terms together. Real terms together is this guy, the real part, and all the j terms with the omega is going to be this term. With the omega is going to be that term. That's the imaginary part. Voila, you got your impedance having real part and imaginary part. Now comes the second part of the question where you need to go ahead and substitute omega equal to 2 pi f. So when omega equal to 2 pi f with 900 megahertz being f, when you substitute in, it becomes 3.562 into 10 power 9. When you go ahead and substitute, it is tedious. You can use your calculator in the complex mode and you can substitute the value to figure out the real part, which is a small number, and an imaginary part, which is 39.4 ohms. So that's the impedance that you're looking at when you see this, right? Turns out that, is it an inductive or capacitive? How do you make the decision? Remember, for an L, it is j omega L. For a capacitance, it's 1 over j omega C. 1 over j is equal to negative j. So this, I can equivalently write it as negative j over omega C. So that's why I say, when you have an inductor, when this is my x, isn't it? So if I were to say, if the component is L or a C, and then if I were to look at x, then this x is going to be omega L, whereas here it's going to be 1 over negative 1 over omega C. If the component is L, then you get omega L. That means the reactance is positive. If the reactance is negative, omega is always positive, yeah? Omega is always positive. C is always positive. You can't have negative capacitance. You can't have negative inductance. So this means clearly the x is, so this is x is greater than 0. This is x is less than 0. X greater than 0 means it is inductive, since the reactance is positive. If x is negative, then the load is capacitive in nature. Yeah.